Why don't
Does
I
everyone
watch
have
my
a
list of
dreams?
dreams?
And
How do I
get
get myself to dream sometimes? I don't want to keep a journal.
Why do we dream? That seems to be the ultimate question. A question which I don't think, unfortunately, we'll have an answer to for quite some time. But the hope of this episode is to go into some of the theories and the propositions that scientists and philosophers in the field have proposed as to why we may be engaging in dreaming when we're asleep. I hope that intro wasn't too bothersome. It was intended to sort of give the impression that there's a great many questions that we all have about the whole experience of dreaming. And the point of this episode is to explore that and all the work that's been put into answering that question and exploring some of the more scientific aspects of it. And I hope you'll stick around and learn with me and enjoy the process. Welcome to the Mind the Gap podcast. Theories attempting to ascribe a sort of purpose or teleological end to dreaming seem to be as numbered as there are scientists investigating the question. The speculation dates back millennia and definitely hasn't slowed up since. So let's examine some of these theories. According to the activation synthesis theory, dreams are caused by widespread random activation of neural circuitry. This random brain activity mimics incoming sensory information that we would receive in our waking states and consists of pieces of stored memories, current and previous desires, and other such experiences. However, they're represented neurochemically. And our brains stitch this mumbo jumbo together to result in a dream which is usually quite bizarre and has a characteristic vague familiarity to it. Now, Freud, of course, we're going to talk about Freud. If we're talking about dreams, Freud separated dreams into their manifest content, what one actually hears and sees, and their latent content, the underlying significance of dream elements, ultimately implying that we dream to fulfill subconscious desires. Graham Mitchison and Francis Crick, yes, that Francis Crick, the DNA structure guy, proposed a reverse learning theory of dreams in their interesting 1983 paper published in Nature called The Function of Dream Sleep, in which they suggest that dreams allow our brains to sift through and prune information that is unnecessary. Now, perhaps dreams are basically a random screensaver our brains generate in order to prevent itself from completely shutting down, as the continual activation theory suggests. Or maybe dreams are the remnants of some evolutionary advantage afforded to us to role-play and rehearse potentially life-threatening scenarios, a la primitive instinct rehearsal theory. A good number of experiments suggest that dreams enable psychological or emotional adaptation and have a sort of restorative and therapeutic aspect to them that facilitates convalescence of psychological trauma. Proponents of the problem-solving dream theory might speak to the usefulness of dreams in allowing the mind to think in much more creative ways uninhibited by the stubborn orthodoxy of our waking minds. The Committee of Sleep, a good book by Dr. Deirdre Barrett, provides some interesting examples of this faculty of dreaming in disciplines such as music, painting, literature, medicine, etc. Paul McCartney states his hit song Yesterday came to him in a dream, and Dmitry Mendeleev reported a dream-inspired construction of the periodic table. Or maybe, as the overfitted brain hypothesis argues, animals are too good at learning and are at risk for rigid overfitting of the learning they do in their conscious lives. Or that is to say that they can't generalize the learning in their conscious lives to unexperienced situations, sort of like a computer or machine that can't extrapolate well outside of its training set. And dreams are sort of, according to this theory, needed to inject a sort of stochasticity or randomness to help us be able to generalize and act in such unforeseen and unexperienced circumstances. Or are sleep and dreaming simply the price the brain must pay for plasticity? As those are the times when the synaptic and cellular processes that had been most challenged during our waking hours are reestablished, as the synaptic homeostasis hypothesis argues. Or perhaps we are making much ado about nothing, and as we humans tend to do, and dreams really have no purpose at all and are just a mere epiphenomenon of the chemical and electrical goings on of the sleeping brain. So whether you take the nihilistic perspective, the encompassing perspective, or try to unify those theories, or choose to be a proponent of a specific theory, it's definitely evident that our understanding of the why of dreaming seems to be as clear as mud. And if you ask me, I would say ultimately the question is less which group is right, but how we can unify these theories. The issue there is that the study of dreaming is limited inherently by the differences between the brain and the mind, the age-old dualist question. Dreaming definitely has a neurological component, but it's still a very highly subjective experience, as are most phenomenon and things we experience in our conscious lives. And as of yet, science hasn't figured out a way to circumvent this subjectivity problem. So maybe let's focus on a topic that's much more. There's much more scientific consensus. The neurophysiological mechanisms that underpin the process of sleep and dreaming have been under rigorous scientific investigation for a good few decades now, and thanks to that fact, we're much more aware of the routine of sleep and dreams and what's going on in the brain that enables these processes. The scientific analysis of what's going on sort of got its start in the mid-20th century with the founding fathers, as it were, Nathaniel Kleitman, Bill Dement, and Eugene Aserinsky. There was some studies on dreams and sleeping before then, but this is when it really started to get serious, and rapid eye movement sleep came into the fore. While more than half a century of intense investigations has yet to provide an unequivocal answer to the questions of why we sleep or dream, we have been able to understand the basic neural underpinnings. So sleep is divided into two main categories, REM and non-REM. The non-REM sleep is further divided into three stages, which are the introductory stages, and we progress through them sequentially until we reach REM sleep, and after which the cycle repeats. So stage one is an NREM sleep, non-REM, and it's the inception of the sleeping process. It's a very short period, typically around 10 minutes, very light sleep, very easy to wake up out of it, and it's a stage where your heartbeat and breathing and eye movements and your muscles start to the electrical impulses to your muscles start to slow down. In fact, you might have noticed sometimes when you're sleeping, you get these little twitches in your fingers or certain muscle groups, and that's sort of your muscles spastically firing before they sort of turn off. And so when you're awake, the brain waves that are measured by an electroencephalograph are sort of all over the place. They're characterized by what are called alpha and beta waves, and when you're entering stage one, it's sort of slowing this down, and the waves sort of become more synchronous and a little more sinusoidal instead of desynchronized and random. So after stage one, we have stage two, which is basically a furtherance of the processes in stage one, and it's also NREM, and your muscles start to have less impulses, your heart rate and breathing slow down even more, your eyes are more stationary, and your body temperature drops as well. Stage 2 is where we spend most of our sleep cycle in, and then comes stage 3, which is the final um, um, non-REM stage, and it's the period of deepest sleep. It's also called slow wave sleep because this is the point where our brain waves become most synchronous and sort of uniform or have like a typical pattern to it. So when this stage is reached, we've basically entered the void. It's at this point that it's hardest to wake someone up, and we've basically completely detached ourselves from the bothers and stimuli of the outside world. Now, the interesting aspect of this stage is that the amount of time we spend in stage 3 is variable throughout the night, and we typically spend more time in this stage at the beginning of our sleep cycle than towards the end. And without the stage, we wouldn't feel as rested or rejuvenated. So if there's some issue with the brain initiating or maintaining this stage of sleep, we people tend to feel very tired and have a difficulty waking up. And now, my friends, we come to the pièce de résistance, the pinnacle, the stage of rapid eye movement sleep, the only one of its kind. While studies suggest that we're able to dream outside of REM, this stage is the big kahuna, the main contender when it comes to studying dreams. Um, it's come to be known by a couple of other names, which give us some insight into what's going on. One of these is D-sleep, which stands for desynchronized sleep. And this sort of gives us the indication that the brain waves at this period are desynchronized. They're sort of all over the place, similar to what might be found in our waking or conscious states. And the other name for it is paradoxical sleep. It's kind of related to what I was just talking about. Scientists refer to the stage as paradoxical because the brain looks very much like it's awake and active, but our bodies are quite the opposite, immobilized. Our muscles are paralyzed. We can't move at all. And that's important because this allows us to not act out our dreams. If our brains didn't inhibit our muscle activity during REM sleep, we'd probably be doing a whole host of dangerous things to ourselves. And while these are interesting names, I'll probably just refer to it as REM sleep. And REM typically begins around 90 minutes after falling asleep, after which our eyes start rapidly darting from side to side. Our breathing becomes faster, our heart rate's more irregular, our blood pressure rises, and the fun stuff happens in this stage. So now that we got the structure, the fundamental structure of sleep out of the way, let's talk about, as briefly and as simply as possible, the brain structure is important for sleeping and dreaming. So we'll start from the bottom and work our way up. And sort of as a disclaimer before I start, I just want to make sure it's clear that these brain structures are not solely, the functions that I'm going to be talking about in regards to these structures is not their only purpose. The brain is marvelously complex, and the different regions, while they may be highly specialized in some activities, definitely are involved in others. So it's important not to view them as a monolith or non-dynamic or static in their functions. Now, that being said, let's start from the bottom. The brain stem is an ancient structure, by which I mean it controls the most basic processes of life and physiology. It helps regulate our heart rate, our breathing rate, our body temperature. It's involved in motor and sensory regulation. And in that regard, within our brainstem are some important structures for sleeping and dreaming, namely the pons and the medulla, which are very important in REM sleep and making sure our muscles are inactivated. The hypothalamus is important in getting and keeping you asleep. Plays a very important role in helping to regulate hormonal signaling, and it's a tiny cluster of neurons which forms a structure that lies basically at the center towards the base of the brain, and it's used in modulating the endocrine system for hormones and acts as a control center impacting sleep and arousal. So within the hypothalamus is a substructure known as the suprachiasmatic nucleus. It derives its name from the fact that it sits atop the optic chiasma, the junction where your optic nerves cross and send the information to the opposite side of your brain, so that we can process our visual world. So that's why it's called suprachiasmatic, because it sits on top of that chiasma, that crossing of the optic nerves. And it gets the nucleus part of its name from the fact that it's a small subcluster of neurons that's in the central nervous system. When you have a grouping of neurons that are highly specialized or have a role in some activity, they're usually referred to as a nucleus. So this region receives information about light exposure, which makes sense. It's sitting right on top of the optic nerves, and it helps to regulate our circadian rhythms by communicating with the pineal gland and other hormonal regulating centers to release hormones such as melatonin, which help get us and keep us asleep. Okay, so next comes the thalamus, a much larger structure than the hypothalamus, which sits right above, and this is sort of where the hypothalamus gets its name. The thalamus is the brain's sensory regulation unit, and it relays the sensory input from the lower levels of the central nervous system to the higher levels, the cerebral cortex, the executive processing unit of our nervous system. So during NREM stages, the inhibitory neurotransmission processes, that is to say that this chemical signaling or the neurotransmitters that lead to inhibition of electrical signals and action potentials, the main one of which is GABA, which I believe stands for gamma aminobutyric acid, something along those lines, but that's the main inhibitory neurotransmitter, and that neurotransmitter, among other inhibitory ones, become prevalent during NREM stages, and this allows our brain to sort of quiet down and tune out the hustle and bustle of the outside world, and helps us fall asleep. So, however, during REM sleep, the opposite happens. We have more excitatory neurotransmission going on, and it allows our brain to become more active and sort of helps paint our dreamscapes, and allows for the visual, auditory aspects of our dreams. The amygdala and hippocampus are two important structures which are part of a larger group of structures in what's called the limbic system, an important set of brain regions which help us regulate emotions and store and retrieve memories. The amygdala is more implicated in the regulation of the emotional stimuli, and the hippocampus is more important for memory formation and retrieval. Both of these structures play a key role in rapid eye movement, sleep, and the emotionality and memory relevance of our dreams. The reason why our dreams can seem so nonsensical and yet somehow tie into our past experiences and have that sort of vague familiarity I talked about with the activation synthesis theory is because these regions are implicated and are not inhibited or regulated as much by downregulated as much by the executive processing unit of our brains, the cerebral cortex. So, many of you may be wondering, as I was, what the purpose of our rapid eyes movement, part of the rapid eye movement sleep stage is, and how that's controlled, and how it may be causally related, if at all, to our ability to dream. Well, as it turns out, there's been some research in the area, and suggests that basically it's our way of our sleeping brains scanning the dreamscape. So, a research study published in Nature Communications in August 2015 from a Thomas N. Dreon et al. Studied 19 neurosurgical epilepsy patients, individuals whose epilepsy was so bad that they had to get a surgical implant to control their brain's electrical activity. And that study demonstrated that the activity of neurons in a region called the medial temporal lobe, which is a network of cortical substructures important in memory formation and retention and emotionality, and includes the structures that we just talked about, the hippocampus and amygdala, among others. And so the neural activity measured during REM sleep in the neurons in that region matched the activity seen during cicadas in visual phenomenon in the waking state. So cicadas are the microscopic tiny movements that our eyes engage in our waking states as we move our eyes from side to side, or even if we're just staring at one thing, and they sort of help our eyes prepare for movement and to move to different areas and to have a current and dynamic processing of our visual environment. So the researchers interpreted this finding as indicating that our eye movements while in REM sleep represent unique points at which our brain's activity during this period and the associated visual like dream imagery processing is updated. So basically, to put it in a sort of more metaphorical analogy, basically each time our eyes move in REM sleep, it's sort of like the refresh rate of our dreamscape television. So this is a very interesting study and very interesting finding, and I had always been sort of perplexed on that, like why our eyes move so much during REM sleep. It seems sort of unnecessary or kind of like a weird phenomenon, and I found it very interesting to find that maybe this is the way that our brains are just refreshing our dream imagery. So my friends, that is some of the basics. I think I'm going to leave it there. Might release some more episodes on some more aspects of dream and sleep research, but for now that seems like a good amount. I don't want to make this go on too long. Hopefully you found that interesting. If you have any questions, please shoot me an email. That would be great. Or leave if you just want to leave some constructive criticisms, maybe some hate mail. Everybody's got to get a little bit of hate mail now and then. And yeah, thanks for your time. I really appreciate it. And until next time.